All right, so with regards to this, we're going to have, oops, starting in, okay, I don't know what that is. There we go. All right, so stock. We're going to create a minimum variance portfolio. You can create as many of these portfolios as you want, but for this case, we're going to do we'll do a minimum variance portfolio. We're going to do a market portfolio. We'll maximize return and call it a day. So we've got Loon, UFO, Stop, LOL. Below here, we're going to have our sum weights. We'll have the expected return of the portfolio and the standard deviation. So the weights that we're going to have these are going to be listed in these cells. Okay, so for now, I'm just going to put 25% in all of them. And then this is going to auto sum across. The expected return is going to equal, we'll do a sum product. Well, actually, in this case, we can't again because of how it's laid out. So we'll need to do equal 25% of loan multiplied by the loan expected return anchored plus, and do that pretty much for each of these. Okay, so that's our expected return. Now for the portfolio standard deviation, this is going to be a little bit of a complicated formula. Let's try this and see if we can get it to work. So actually what we're going to do is we're going to use the FAME function underscore portfolio. Get the portfolio return, portfolio variance. We're going to start off, we'll do equal square root and then port FAME, excuse me, port this variance one. Let's look at that one first. What does that have? So that'd be our variance, covariance matrix, and then the weights. Let me cancel out that because we have, actually that is what we did last time, variance, covariance matrix. So I'll do that again. Equal square root FAME, parentheses, whoops, FAME underscore port 1, variance 1. So we need the variance covariance matrix. So highlight this data, we'll anchor that, and then our weights will be these. Drag that across. Perfect, because they're all should be the same. So now we're going to use Solver to help us figure out what the weight should be. So I'm going to go to Solver. And I'm going to set the objective. I'm going to minimize it by changing these. And at this juncture, I'm not going to worry about, let's see, those only one constraint. This has to equal 1. Click OK. And this one, I won't make it non-negative. We'll solve. And you'll see that we get that solution. We'll keep that. Next thing we'll do, kind of get at the market portfolio. So I will solve again, but this time make the unconstrained variables non-negative. And we're going to change now this one. And we'll be changing these. So now the objective is to minimize that one, C17. So now we'll solve. You see that result. And then to maximize the return, so now solver, excuse me, will maximize now D16. We won't make the constrained variables not negative, and we'll do that by changing these weights. So now I'll solve. Okay, that didn't converge. Okay, so restore and return back. So let's make them non-negative and solve again. Interesting. So we're maximizing return by changing these variable cells. Subject to the weights have to equal 1. All right, let's change it from GRG nonlinear to simplex. That may sometimes have something to do with it. Still no solution. And evolutionary. All right. So we're going to keep what it found, even though it does not look. Has some issues there. Let's see what it's. Okay, so yeah, so it's not converging at all. Okay. All right. So we're going to leave this one out. The efficient frontier, you really just need at least 2 points, but you can do this for multiple, and typically you can change the standard deviation level to kind of set and then find what would be the best for that. But the efficient frontier is graphing standard deviation and expected return, and it's giving you the minimum standard deviation and then the highest expected return for each of those portfolios. So now at this juncture, what I can do is I can highlight these. I can insert chart. So we could get some of that effect, but the more points, it would eventually curve out.